Alrighty, we are back and here we go. We're going to talk about enthalpies of formation now. Okay, and so there are other types of enthalpy calculations to be aware of. Okay, so there's delta H of vaporization. That is the enthalpy of vaporization, which is the amount of energy it takes to turn something into a gas. Okay, so it's the amount of energy required to turn something into a gas, so that's that. Close that or minimize that so you don't see it. The delta H of fusion, that's the enthalpy of fusion. And that is the amount of energy it takes to melt a solid. Okay, the combustion, delta H of COMB, that is the enthalpy of combustion. And that's the amount of energy it takes to combust a sample. Another one that we would look at would be the delta H of the delta HF, which is the enthalpy of formation. And that's what we're looking at right now. The delta H of formation, or the heat of formation, is the enthalpy change for a compound when calculated based on the enthalpy of its individual atoms. Okay, and so what we can do is we can actually look these up for elemental standards in an appendix in your book, in the back of your book, and we can add these pieces up. So let me show you what that means, okay? So because of all the variability in the conditions, chemists realized that we needed to set a standard set of reaction conditions. And so when we did that, they came up with the standard enthalpy change. And so standard enthalpy change. And that is the delta H with the little degree sign. Okay, so the standard enthalpy change does this through being listed, the listed enthalpy change for compounds at 298 K and 1 atmosphere of pressure. And these are just standard temperatures and pressures. You guys remember that from gases last year. Okay, and so it's the same thing. We just said, okay, if we put everything at those temperatures and those pressures, we're going to use energies related to that and how those that are calculated at that. And so that's going to figure out how we do this. Okay. And so what that came up with is the standard enthalpy of formation. And so here we go. So this pen is more squeaky than the other. I'll switch back here, I'm sorry. So the standard enthalpy of formation, there we go, you can see it a little better. So the standard enthalpy of formation, the delta H F degree sign, is the change in the enthalpy for the reaction that forms 1 mole of the compound from its elements with all substances in their standard states. And so this is where we are going to start looking at that. So this is from its elements with all substances in their standard states. And so the reactions for these are written so that 1 mole of the substance is created as a product. Okay, so that 1 mole as a product thing might end up making some weird nomenclature in the front. We're going to end up with fractions in terms of reactants, or we may end up with that. So just something to think about, okay? And so by definition, delta H of formation is the most stable form of any element is 0. And so when I say we're looking at elements, we're looking at as they appear on the periodic table. Okay? So your friend and mine, the ultimate party planning guide, the periodic table. So if I look up the delta H of formation for, I don't know, nitrogen gas, well, that's going to be a 0 because that's what it looks like on the periodic table. If I look up the delta H of formation for iron as a solid, well, that's going to be 0 as well because iron is found as a solid. Now, if I changed nitrogen to a liquid, well, that means that I had to change the amount of energy in that system considerably. I had to remove a whole bunch of energy to cool that nitrogen down to make it a liquid. And so it's no longer going to be 0. And so we'd actually have to look for that, and we'd have to account for that temperature change to get to those spots, or those phases, and those different temperature settings. And so that's all I'm looking at right here, okay? So just pay attention to that, and you'll be good to go. So elements in their standard state makes 1 compound, 1 mole in a standard state. So the delta H of the reaction for that is equal to the delta H of formation. Okay, and we're going to find the values for these compounds in our appendix, in the textbook, or in the table in this chapter. And so we're going to find everything we need right there, and so that's where we're going to end up working on that. Okay, now to be able to do this, we have a big ugly equation that we're going to work through. And so let me show you what that big ugly equation looks like, and let's figure out how to use it right away. Okay, it looks really, 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 really ugly, but it's not. It's kind of a chill equation once we figure out how to do it. Okay, so here we go. So the delta H of the reaction is going to equal, alrighty, so this is going to be the Greek letter sigma, and I'm going to go really slow so my sigma doesn't look bad because I have a hard time drawing sigmas. Is going to equal sigma n delta H of formation of products minus the sigma n times the delta H of formation of the reactants. Okay, delta H means sum. N and M, I'm sorry, this should have been an M, not an N. Sorry, wrong textbook, are the stoichiometric coefficients. You'll see what that means in just a second. Now, like I said, this looks really complicated, but all you're really doing is adding up the heat of formation of all the products and then subtracting the sum of all the reactants of the heats of formations of the reactants. And that's really all you're doing. Okay, so it looks exceedingly complex and ugly, but you're going to like it when you see it because it's really not such a big deal. Okay, so let me show you what that looks like. Okay, so we're going to switch to a sample problem, and I'm going to scroll this down. There it is. And we're going to erase this mess. Actually, I could have left it, couldn't I have? Oh well, I didn't. So you have that reaction. You're going to see it up in your notes above, and we're going to go from there. So what's the standard enthalpy change for the combustion of 1 mole of benzene, C6H6 as a liquid? So we need a combustion reaction first. So let's write our chemical reaction. So we have carbon, 6, H6, liquid phase, plus oxygen. This is a gas. It's going to make CO2, gas, plus H2O as a liquid. Okay, now we're going to balance it. So this is a 1. This is going to be 15 halves of oxygen. This is going to be 6. This is going to be 3. Okay, and once again, we're ending up with weird stoichiometric coefficients because we need this to be a 1. Okay, so this is 15 halves. Hopefully you can see that a little bit better. Probably not. 15 halves. There, now you can see it. Okay, so we're going to use that big ugly reaction, this thing, the delta H of reaction, with our little 0 is going to equal the summation n delta H F of products minus sigma m delta H of formation of reactants. Okay, so that's what we're using, and first thing we want to do is write out our pieces and the numbers that we need and go from there. Okay, so delta H of reaction, is going to equal 6 times the delta H of formation for CO2 plus 3 times the delta H of formation for water minus the delta H of formation, so it's going to be square bracket here, 1 times the delta H of formation for C6H6 plus 15 halves times the delta H of formation for O2. close square bracket. Hopefully you can see that. Not very well. Bummer. Pen's probably not happy anymore. Okay. Oh, 2. That's a little better. Sorry. Okay. So now I have 6, 3, 1, and 15 halves. This HF of CO2, I'm going to look that up. HF of water, I'm going to look that up. HF of C6H6, I'm going to look that up. And HF of oxygen, I'm going to look that up. So now I'm just going to put numbers in. And that'll be what we need. Okay? So now, first one is going to be 6 times the delta H of formation of CO2, which is negative 393.5 kilojoules per mole. Okay? This number is in moles, because that is the stoichiometric coefficient, so those are moles. Okay? Actually, I'm going to rewrite that one and move it over a bit so I don't have quite as much space. I'm sorry. So delta H reaction is going to equal 6 times CO2, 393.5 kilojoules per mole, plus 3 times the energy for water, which is negative 285.8, the heat of formation for water, and that's kilojoules per mole as well. Square bracket. This blue one I think is dead now too. Let's try this one. Minus, square bracket, 1 times negative 49.0 kilojoules per mole, okay, I think we're done with blue today. Let's moving on, different color. Plus, okay, you can see it's green, plus 15 halves times 0 kilojoules per mole, because this is oxygen in its natural environment. Okay, so there we go. So that's our basic equation, square bracket, end of bracket there. So delta H of reaction is going to equal 6 times this, negative 393.5, which is going to be negative 2361, minus 857.4 kilojoules, minus 49 kilojoules. And so this reaction is going to be negative 3267 kilojoules. Okay, and so that's how we could do that by using a heat of an enthalpy of formation. So that's how that one works. Okay, so there we go.